Hello students, hope you are keeping yourself safe and healthy during this lockdown period. I am Dr. Ashma Srivastav from Department of Chemistry, JSS Academy of Technical Education, Noida. In continuation to my lecture series on molecular orbital theory, this is my last lecture on the same topic. In today's lecture, I'll be discussing about metallic bonding and band theory. This lecture has several learning objectives. Number 1, basic understanding of metallic bonding. Number 2, differentiating it from covalent and ionic bonds. Number 3, two theories of metallic bonding. Number 4, molecular orbital model of metallic bonding, which is also called band theory. And lastly, we will discuss the classification of materials on the basis of band theory. Now, what is metallic bonding? Just like covalent and ionic bonds, it is also a type of chemical bonding. But here, the bonding is existing between the atoms within the metals. It is the electrostatic force of attraction between the electrons which are delocalized, which are called conduction electrons, and the fixed positively charged metal ions, which we also call kernels. With the help of this type of bonding, we can satisfactorily explain the various physical properties of metals such as their strength, malleability, ductility, thermal and electrical conductivity, etc. Now, why or how this metallic bonding is different from ionic or covalent bonding? In case of metallic bonds, they are formed by the attraction between the metal ions and the delocalized free electrons, whereas ionic bonds are formed by the transfer of electrons from one atom to another, leading to the formation of cations and anions, and the electrostatic force of attraction holds them together. In case of covalent bonds, there is sharing of electrons taking place between the combining atoms. Now, one of the important aspects of metallic bonding is that it is non-directional, because the electrons are not shared with one atom in one direction. However, they are shared with many other neighboring atoms in all directions. In contrast to this, covalent bonds are directional in nature. Since the atoms prefer specific orientations in the space relative to one another in order to minimize the bond pair lone pair and lone pair repulsions. As a result, molecules in which the atoms are covalently bonded have definite shapes. Ionic bonding is similar to metallic bonding in this sense, and it is also non-directional because an ion has the same attraction from all the direction for an ion of opposite charge. The number of anions surrounding a cation is limited by the charge of ion, by their size, and the efficiency of lattice packing. Now let us discuss the two theories of metallic bonding. With the help of these two theories, we can explain most of the properties of metals. And these theories do not involve directional bond formation, which we had said in the previous slide that they are non-directional. The first theory is called free electron theory or electron C model, and the theory number 2 is the band theory. free electron theory or electron C theory was given by Lorentz, and the main features of this theory are that metal is supposed to consist of two parts, valence electrons and the remaining part including nucleus and inner shells, and that is termed as kernel. The metallic crystal consists of closely packed metal atoms in three dimensions. Kernels of the metal atoms occupy the fixed positions called lattice sites, while the space between the kernels is occupied by the valence electrons. This type of arrangement of valence electrons and kernels is shown in the next figure. Now you can see in figure number A that we are having the kernels which are occupying the fixed sites, and the free electrons are wandering here and there throughout the lattice. So we can say that metal consists of cations held together by negatively charged electron cloud or glue. Now let us see figure B. In this figure B, we can observe that the electrons are moving rapidly in response to the electric field, and that is why metals are good conductor of electricity. In figure C, there is application of heat at one end of the metal and it is transmitted towards the other end through the kinetic energy gained by the electrons, and thus it also explains that metals are good conductor of heat. Figure D is showing the ductility of metal. The layers of atom in metal are hard to pull apart because the electrons are holding them together, and that is the reason for their immense strength. But the individual atoms are not held to any other by specific atoms. That is why they slip easily past one another when force is applied. Now we have come to the band theory, which is extensively used to explain metallic bonding. This theory is based on molecular orbital theory, and that's why we are studying this theory under the topic of molecular orbital theory. This theory is the application of molecular orbital theory on solids. Now, what we consider in band theory is that the overlapping of atomic orbitals of all the metal atoms give rise to n number of molecular orbitals. Now we will explain it by taking the example of one metal, and let us take sodium as our example. Sodium, as you all know, is having the atomic number 11 and its electronic configuration is 1s2, 2s2, 2p6, 3s1. Now 3s1 is its valence shell, and in this valence shell one electron is present. The sodium crystal is formed by the gradual addition of n number of sodium atoms. Now we will see the molecular orbital model of sodium on the next slide. So in this figure, what we see in figure A is the combination of two sodium atoms, and starting from 2 atoms we'll go up to n atoms for forming the sodium crystal. Now let's start with the addition of 2 atoms. 2 atoms, atom A1 and atom 2, and since the valence shell electrons are involved in the formation of bands, so 3s orbital is going to participate in the formation of molecular orbitals. 3s orbital of this atom is having 1 electron, and since 2 atoms are combining, so we have shown two 3s orbitals containing one electron each. Upon the combination of these two atomic orbitals, there will be a formation of two molecular orbitals, out of which one will be bonding and the other will be anti-bonding. Now these two electrons of two atoms will be accommodated in the bonding molecular orbital, because bonding molecular orbital is having lesser energy than the combining atomic orbitals and also lesser than the anti-bonding molecular orbitals. So these two electrons have entered into the bonding molecular orbital. Now you just see the energy gap between the two. It is considerable between the bonding and anti-bonding molecular orbital. Now let us move our discussion to the combination of three such atoms. When three such atoms are combining, so we are having three 3s orbitals. They will combine to form three molecular orbitals, and the first two electrons will enter in the bonding and the third electron will be singly paired and it will enter in the non-bonding orbital, and the anti-bonding orbital is vacant. Let us add the another atom to the same Na3. Na3 plus one atom is Na4. So 4 atoms are going to combine. These 4 atoms each are having one 3s orbital in which one electron are present. So total 4 electrons are present in these 4 3s orbitals. Now 4 atomic orbitals are combining. The number of molecular orbitals that will be formed will be 4 only, and half of which will be bonding and half will be anti-bonding. This is the characteristic feature of molecular orbital theory which we have learned in the first lecture, that atomic orbitals combine to form molecular orbitals and the number of molecular orbitals that are formed is equal to the number of combining atomic orbitals, and half of them are bonding molecular orbitals and half are anti-bonding. So 4 atomic orbitals have combined, so there 4 molecular orbitals are formed. Half of them, that is 2, are bonding and the next half is anti-bonding. Now we have to accommodate the 4 electrons in these bonding and anti-bonding orbitals, and they will be accommodated in the first two orbitals, that are bonding orbitals. So bonding and anti-bonding orbital will anti-bonding orbital will remain vacant. Now in this case, the conduction of electron has to take place between the highest occupied molecular orbital to the lowest unoccupied molecular orbital, and that is the second bonding molecular orbital and the first anti-bonding molecular orbital. What I said, conduction of electron, if it has to take place, it will take place between highest occupied molecular orbital, that is molecular orbital number 2, and lowest unoccupied molecular orbital, that is molecular orbital number 3, that is anti-bonding. So the conduction is going to take place between second and third molecular orbital, and you can notice that the energy gap is reduced from Na2 situation. In case of Na2, there was a considerable energy gap between bonding and anti-bonding molecular orbital, and if the conduction has to take place, there was a very large energy gap. But in case of Na4, this energy gap is reduced between HOMO and LUMO. Now let us come to the last situation where n number of atoms of sodium have combined to give n number of molecular orbitals. N atomic orbitals of sodium, that is 3s orbitals of sodium, are going to combine to form n number of molecular orbitals. And out of these n number of molecular orbitals, n by 2 will be bonding molecular orbital and n by 2 will be anti-bonding molecular orbital. It means that half will be bonding, half will be anti-bonding, and this we are observing since the beginning. Now, the molecular orbitals that are formed, they are very closely spaced and even they are overlapping with each other. So the energy gap between the highest occupied molecular orbital and LUMO in the case of sodium crystal has very negligible, or it is not at all present. So it means they are merging, and we can say that the separation of molecular orbital is decreasing as the number of sodium atom increases, and it leads to the formation of closely spaced bands, and therefore this theory is called the band theory. So the molecular orbital which are formed in NaN case, that is in the case of sodium crystal, in this case we are getting closely spaced molecular orbitals, and these closely spaced molecular orbitals constitute the band. This is the valence band which is formed, which is half filled and half empty. Now the band formed by the valence electrons is called the valence bond, as I suggested or as I told you right now, and that which is formed by the molecular orbital combination of 3p orbitals which are vacant of sodium is called the conduction band. So in this figure I have tried to show that 3s orbital which 3s orbitals of n atoms of sodium combines to give rise to a valence band which is half filled and half vacant, and conduction band is formed from the overlap of 3p orbitals which are vacant, and that's why the conduction band is empty. Now these valence band and conduction bands are overlapping, and hence the HOMO and LUMO are very near to each other, or they are also overlapping. So the conduction of electron will take place without any effort, without any energy, very easily. Now on the same lines, we can talk about the molecular orbital diagram of magnesium. Magnesium is having the electronic configuration 1s2, 2s2, 2p6, 3s2. So 3s orbital is going to participate in the formation of bands or in the formation of molecular orbitals. In case of Mg2, 3s2, 3s2 of atom 1 and atom 2 are combining, leading to the formation of bonding and antibonding molecular orbitals. Now since there are 4 total electrons in atom 1 and atom 2, so we will be filling all those 4 electrons, and hence bonding as well as antibonding molecular orbitals will be completely filled. Now let us see the situation of Mg3. Here 3 atoms of magnesium atoms are combining, and we will be getting 3 molecular orbitals, and all will be completely filled. This is Mg4 situation, in which all the molecular orbitals, half bonding, half antibonding, are formed, which are completely filled. Now when the magnesium crystal is formed by the combination of n atoms of magnesium, so there will be n number of molecular orbitals that are formed. Half will be bonding, half will be antibonding, but all are filled. So here also we get a band, and this yellow color represents the valence band, and this valence band here is completely filled. Now how to account for the conductivity of magnesium when the valence band is completely filled? HOMO is available on the top of this level, top of this band, but where is the conduction band? Where is the LUMO? So the LUMO or the conduction band is obtained by the overlap of 3p orbitals. So 3p orbitals are going to overlap, resulting in the formation of conduction band. It is similar to that which was formed in the case of sodium also, But how this figure differs from sodium? In case of sodium, the 3s orbitals have resulted in the formation of valence band that was half filled and half vacant. Whereas in case of magnesium, this is completely filled. And this valence band is overlapping with the conduction band, which is formed by the overlap of 3p orbitals, which are vacant. I hope the concept is clear to all of you. Now a question for you. Think about the molecular orbital model of aluminium, which is having the atomic number 13 and the electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p1. So how you are going to account for the formation of valence band and conduction band in this case? Give your answer in the comment section. I am waiting for them. Now we have come to the last topic of our lecture, and that is band theory of solids. With the help of this theory, we can classify the materials into three categories, which are conductors, semiconductors and insulators. Conductors we have discussed right now. Metals are the conductors, and as we have noticed that there is no band gap between the valence band and the conduction band, since these bands are overlapping. How we have explained the formation of valence band and conduction band? We have explained it with the help of molecular orbital formation. And since these bands are overlapping, there is continuous availability of electrons in these closely spaced orbitals, and hence electrons can be easily transferred without any effort, as I mentioned earlier. Semiconductors, they do have a small energy gap of 0.7 to 1 electron volt between the valence band and the conduction band, and electrons can make the jump from Vb to Cb, but not with the same ease as they do in conductors. This energy gap leads to insulation at ordinary conditions, but on heating or doping with certain elements, or which are the impurities, they function as conductor. Now what are insulators? They have a huge band gap which is larger than 3 electron volts between the valence band and conduction band, and in this case the conduction of electrons is not at all possible from Vb to Cb. Now in this figure I have just summarized the content which we have discussed in the previous and in the top of this slide. There is overlapping of conduction band and valence band in conductors, a considerable energy gap in case of semiconductors and between the valence band and conduction band, but it can be reduced by doping. And third is an insulator, in which there is a very large energy gap existing between Vb and Cb. Now before concluding the class, we will also touch upon the various types of semiconductors. Semiconductors can be divided into two categories: intrinsic semiconductors, which are pure form of silicon, germanium, etc., and extrinsic semiconductors, which are having the impurity present in it introduced due to doping, and they can be divided into two types: N-type and P-type. Intrinsic semiconductor we have discussed in the previous slide. The same case is applied over here, but now let us put a light upon the N-type and P-type. In N-type, the pentavalent phosphorus or arsenic are added to the high purity silicon for the formation of this type of semiconductors. These impurities are called donors. The energy level of donor is located close to the conduction band, which you can see in the figure. and the energy gap is now reduced. Now the energy gap is between the donor level, which is just below the conduction band. Electrons at this level can be easily excited to the conduction band, and this contributes to the conductivity. Now let us see the p-type of semiconductors. P-type of semiconductors are formed by introducing a trivalent impurity such as boron into the intrinsic semiconductor. This type of impurity is called acceptor impurity. The energy level of acceptor is close to the valence band and it consists of holes. That is, no electrons are present in this level. Now, electrons from the valence band can be easily excited from Vb to that acceptor level, and this contributes to the conductivity of p-type semiconductors. So in n-type semiconductor, conductivity is attributed to the energy gap between donor level and conduction band and the migration of electron from the donor level to the conduction band, which is quite easy since the energy gap is low. And in case of p-type, the conduction of electron is from Vb, that is valence band, to the acceptor level, which also takes place at ease, and it contributes to its enhanced conductivity. This brings us to the end of our series on lectures on molecular orbital theory. Keep reading and I'll come up with new topics very soon. Thank you.